start it again, but I guess there's hardly a way around it. Okay, let's go from current slide. I can't think of any announcements that probably would have any pertinence to this class. I would just say most of the things I get that might be announcements you probably get through your email too. So check your email and you'll probably see the things I would be announcing would be there. So we'll just let it go like that. Any questions on anything we've covered so far? All right. We are in Chapter 12, which is Matter, and the section we're in, I think, is 12.2. It's sort of a long, 12.2, Properties of Solids. And we'll try to move through these fairly quickly. If you recall last time, we talked about a variety of stresses, okay? We talked about certain properties, ductility, malleability, elasticity, and when it came to elasticity, we mentioned the term stress, the ratio of an applied force to a outside force, which tends to cause a distortion to the area over which the force acts. So it's a force per unit area. All right. Where we're starting today is a look at 5 of the basic types of stresses. So these all follow that same concept of force per unit area. And the first of these, let me get my pen set up, if I can get the pen set up, okay, is a tension. Now, I thought there would be a slide with this on it. There really isn't. But basically, the figure they have in the text is a tug-of-war. Each side is creating a tension on one end of the rope, pulling against the other. That's a tension. It's a force. The pull per unit area would be the diameter of the rope. Okay? So if you had, even if it wasn't a rope, a pipe, anything such as this, and you're exerting a force in opposite directions, then the force divided by the cross-sectional area is your tension. Force per unit area. Typically measured in the U.S. customary, force is measured in pounds per usually square foot, okay? But it could be square inches, like PSI, pounds per square inch. It could be any other length measurement, but usually between square feet and square inches. In the SI unit, then that would be a Newton per square meter, okay? And here's a problem, okay? A pound is a larger force than a Newton, but a meter is a much longer distance than either feet and certainly than inches. So a Newton per square meter is a tiny, tiny amount of tension or any of the other stresses. So usually a Newton per square meter is also called a Pascal, and since that's such a tiny unit, we quite often refer to it in kilopascals, okay? So either pounds per square foot or pounds per square inch, and this one would be pounds per square inch would be PSI. That's a unit of stress, tension, or any of the others. And Newton per square meter, which would be a Pascal, but quite often measured in thousands of Pascal because a Pascal is so small. Like when I closed the door, when I came in, that increased the pressure in the room by probably a few pascals. Did anyone's ears pop when I did that? No. Pascal is way too little. You didn't even measure it. Okay? So let's go to the second of these, and this is compression. And it's almost the exact opposite of a tension. A tension is a stress caused by pulling directly opposite each other. A compression is caused by two forces acting directly toward each other. So this would be, and I'm going to leave this slide now to go to the other, and this shows a compression, okay? A bridge over a large body of water, certainly the force of the bridge, the weight of the cars and trucks on the bridge is pushing down, but then the supports, all the building that went underneath it is supporting this by pushing up. That's compression. That stanchion is being compressed, mostly from the weight above, but being supported by the weight above. That's a compression. That's a type of a stress. It's, again, the force, if these are the forces per unit area. Let me get my pen back. It may not make any difference. So this would be the force, and the unit area would be the cross-sectional area of that. So again, the compression would be force per unit area. Okay? And again, same units, pounds per square foot. In this case, I wouldn't use square inches, or newtons per square meter, which is a Pascal. This will be kilopascals or megapascals, because that's quite a bit of force. Okay? You could also represent this by a pipe here, or any kind of a structure here, forces in the same direction, opposite each other, pushing toward each other, divided by the area. Okay? This would be the area here. Okay. Now, another type of force. I think this one's also, oh, okay, there was the one I just was doing. The second example of a compressive force, force per unit area, where the area would be the cross-sectional area here. So the compressive force is equal force per unit area. Compressive stress. Okay. Now, the next one is shear. Okay. In this case, the forces are against each other, sort of like a compression, but with a distance in between. So they're not along the same line. Pushing down on a book or a manual or something like that, that is, not sliding easily across the table, it creates a shear, and that's what we mean by that. Now, the forces, of course, are here. Okay, force here and force there. The unit area here is not exactly clear which it is, but it probably would be the cross-sectional area of the book that would be to that end, down to this end, up, that would be the cross-sectional area. I don't have it drawn very well because his hand's in the way. I can't see how big that is. That would be the cross-sectional area. So a shear stress is in some sense, a twisting kind of, one force one way, one the other, but not in the same line. But again, force per unit area. Okay? Now, the next is even more of a twisting nature, and this is a torsion. Now, there's the force. The cross-sectional area, in my mind, would be the area, whatever this was, going back to the back, this would be the cross-sectional area. Force per unit area. Area perpendicular to those forces. Okay? Now, yeah. Here is a torsion. This is definitely a twisting motion. Okay? The force is in this direction, so that's your force, and the unit area would be the area over which that force is acting, which probably is going to be the area here of the nut. Not the area that you're twisting up here, but the area that's actually being twisted into the wood. So again, force per unit area, that's your stress. Okay? Now, that's not a straight line force, obviously, except that he is pulling in this direction. Now, in a minute, he'll twist around to another direction, but you can measure the force as this force right here, the force of the pull in this direction. Then later it'll be there. So just whatever the tangential force is, that's going to be the magnitude of the force. Usually we can't measure a vector that bends like that. So it's the force at any time. Now, there is one more, and this was, they didn't actually write it here. This is torsion. Definitely a twisting force there. That's the O there. It's pretty ugly. All right. And this is, again, and you measure that force. The symbol for that force is torque. Okay? This is T-O-R-Q-U-E. Okay? The symbol there is tau. That's the Greek letter that corresponds to our T. Okay? And it's difficult for me to tell the way they've drawn this. They look like these torques are in opposite direction. In a sense it is. The resistance down here that you're twisting into and the torque that you're exerting up here, they are in opposite direction. The torque down here is resisting the turn. This is pulling the turn. They have their arrows going the other way. The book was opposite this, so, but they are in opposite directions. Okay. The next is a bending force. Okay. Now, I don't know if this is one of the authors. I think it probably is. And a bending is a combination of compression and tension. Now, that looks a little strange, but down here, the bottom part of the board, the forces are like this, whereas the top part of the board, the forces are compressive forces. The bottom are tensional forces. Okay? And here's the illustration of this. These are compressive forces, and these are tensional forces. And it's a combination of those that results in the bending. Of course, the cross-sectional area would be whatever that was a board, looks like maybe a 1/8 or something like that, so that would be the cross-sectional area there. This would be the area, and you would measure them that way. Don't worry about these. You're not responsible for them. The main thing is that you get the kind of the concepts down, because later we'll be doing exercises from them. And let's see, why is this upside? Yeah, I have it upside down. Okay. And this is Robin? Second? Powell. Got it. Emily. Sorry. Okay. My pen has chosen not to write. So maybe you're not here after all. Okay. This is so aggravating. I got this pen in Montgomery. I don't think anything works well in Montgomery. Ooh, did I say that? Okay. No. All right. All right. So we're down to missing Jordan, Tiara, and Robin. Okay. Hopefully some more will be coming in. We're just talking about some of the different types of stresses that we have. Tension, compression, shearing, torsion, and bending is a combination of compressive and tensional stresses. Okay. Now, those were stresses. The next word or concept that's addressed here is called strain. And what is strain? Okay, strain is the deformation caused by the stress. of an object by the applied force. Or I would say the stress, okay, which is force per unit area, okay? And what a strain is usually a change in a dimension of some nature, okay? This one, obviously, this is a bending stress, and the deformation would be measured in the amount of strain, and that's why they put, originally, when you had this looks like a material you use in a cushion or something like that, and these lines, when this was straight, no stress on it at all, then these lines were lined up perfectly. But when you the bending force, you force these closer together and stretch these out. You can see the stretching here and the compression there, the tension there, the compression there. And that is the strain, is the deformation, the change in the lengths here, the change in the length there. These got shorter, these got longer. The strain is the resultant change in dimension, basically, of your material once the stress has been applied. So I think of it this way. I don't know if you like this or not, but in English, you learn that verbs do the action. To me, that's the stress, the thing that's doing the action. The strain is the result of that. So I think of that as the object of the verb, okay? So you have a subject, verb, and object. The verb is the stress, and the object is the strain, okay? So let's do a problem then. It has nothing to do with the this figure, so I think we'll probably be better off with a on the clean sheet. So let me get out of this and go back to the clean sheet and go back to the current slide and get my pen back. All these steps I have to do. Okay. A steel column in a building that has a cross-sectional area. I don't like the way they put that sentence together. Sounds like the building has a cross-sectional area of 2,500 square centimeters. That would be a very small building, but it's the column, steel column, that has a cross-sectional area of 2,500 square centimeters. Okay? So there's the area of the column, and that would be 2,500. And notice they put a bar over that first zero, meaning how many significant digits do you have? 3, okay? The 2, the 5, and the first 0, and that's an area, so that should be squared, not cubed. Okay, square centimeters. Supports a weight. This steel column is supporting a weight of, and the weight is a force due to weight. That's how we used to symbol. They're just putting F now, but that's what we've used before. Of 1.50 times 10 to the 5th, I believe it is, newtons. Now, 10 to the 5th would mean you would move this decimal 5 places to the right, which would be 150,000 newtons. That's what that stands for, 150,000 newtons, which is a fair amount of force, okay? But buildings have quite a bit of weight to them, okay? It says find the stress on the column. Now, what kind of stress do you think this would be? Weight of the building on the column. Compressional stress, absolutely. Just like the bridge, okay? The weight of the bridge on the column. Now, what seems to be wrong with the picture, though, or with, not the picture, what I've written here? The units. What is messy about the units? What do we usually measure stress in? What units? This is metric or SI units, so that would be pascals or kilopascals. But tell me what a pascal is. Top part is a Newton, that's for sure. But what's the bottom part? Newton per meter squared. We have square centimeters. So we need to convert the square centimeters to square meters. Okay? That's what we got to do first. You don't have to do it first, but I just find it easier to take care of it here. Now notice I've put two blanks there. One is for numbers and one is for units. Always put the units in their place. And this is Kiara. Okay. Now, I think I know the answer to this, but since you were never asked, let me find out. Okay? I don't guess you were ever asked. Do you prefer this to be a 1 2-hour class, or would you rather it be 2 1-hour classes, like Monday, Wednesday, rather than all the class on Wednesday? Which would you prefer, 1 2-hour class? That's what everybody has always said, but I just noticed, I'm guessing some people are coming from work and it's hard to get here at 4:30. So if you wanted to, we could do 2 classes, 5:30 to 6:30, Monday and Wednesday, and that might make it a little easier on you. But if you're okay with 1 2-hour class, I'm fine with it too. What you think? Keep it like that? Okay. I'm recording everything, or at least today I am. Okay. If y'all remember, maybe some of you weren't here, last Wednesday I forgot to turn on Screencast-O-Matic, and I was at the end of the class. I went and said, "Where's my thing to stop the recording?" I thought, "Oh, I never started the recording." So what I'll do, and if you want to hang around and see it, I'll show it to you. What I'll do for when I save today, we're starting in 6.2, and we'll go 12.2. We'll go however far we get, and then I'll look and see the one that I taught last time I taught it. And unfortunately, last time I taught it, they were 1.5-hour courses because it was in the summertime. It was a 3-hour course, and 3 hours was a bit too long, so we did 2 days a week, hour and a half. So it'll be an hour and a half. So it won't cover everything we did last time, but I'll try to hit in fact, I may save 2 classes if they straddle them. So we'll see. But they'll be in a different part. They'll be up at the top part. The current ones are at the bottom part. So if you want to hang around and see that, you can. All right, we were trying to change the units from cubic centimeters to cubic meters. What unit goes? Always put the units in the place. That's the second blank there. What unit goes where? Anybody? Okay, either meter or centimeter. One goes on top, one goes on bottom. Which goes where? Meters on top and centimeters on the bottom. Why? So you can cancel out centimeters here and leave meters right where you want them. Okay? Now, before we mess with the squares, let's find our conversion. How many meters in a centimeter, or how many centimeters in a meter? Centi means 100. So which is 100? How many? Okay. 100 cents in a dollar, 100 centimeters in a meter. Okay, in 1 meter. Now we've got to do our squaring. We're dealing with square centimeters, square meters, so we got to square 100, and if we square 1, guess what? That's still 1. Well, what is 100 square? You double the number of zeros. 10,000. Okay? Now, if you're dividing by 10,000, that's merely moving your decimal, those 4 zeros to the left. So this is 0.250 square meters. You need that extra 0 there because you have 3 significant digits. Okay, you see how that works? All right. Now that we've got the unit set up, we're looking for stress. And what's the formula for stress? Said it several times at the beginning. Force per unit area? Perfect. And what's your force? 1.50 times 10 to the 5/5 newtons. And we could write this in scientific notation, but actually it's probably just as good to write like this, 0.250 square meters. Okay. Now, I'm going to do something a little strange here. It's just because I don't have a calculator. I'll let you see how weird my mind is. I'm going to move this decimal 2 places that way, which means I have to move that one 2 places that way. It hasn't changed anything, except now this will be 10 to the 3rd because I changed that. And 25 will go into 150 how many times? 6 times. And so you have, did I move it right? Yeah, I think so. Nope, I didn't. Now you move. Yeah, that's right. Okay. So that would be all right. 6 times 10 to the 3rd newtons per square meter, which is 6 times, actually, I'm sorry, I should have 0.00 because we have 3 significant digits. 6.00, that's kind of ugly, isn't it? Okay. That was not what I wanted to do. 6.00 times 10 to the 3rd pascals, or oh, I see. Sorry. You don't change this. Okay, you leave that 10 to the 6 because I multiplied numerator and denominator by 100, so that doesn't change my exponent up here. If I had, I'd have to change the exponent down here too, and I didn't have it as exponent. So that's times 10 to the 5th, not 3rd. I knew something looked bizarre there. Okay. 10 to the 5th Pascal. And what's a kilopascal? 10 to the 3rd. So this would be 600 times 600 kilopascals, because a kilopascal is 1,000 pascal. So take 3 of those decimal places, and that leaves you 2 left. So that'd be 600 kilopascals. And all 3 of those zeros, both of those zeros are significant. 600 kilopascals. All right. Now, with that under our belt, collective belts, I don't remember what my next slide was here, so hold on just a minute and let me check. I want to use the slides when I can. We'll get there in a minute. No, we can probably use it. So let's go for this. I'll put the verbiage here. The next topic we're going to talk about in 12.2, I don't know why I keep saying 6, 12.2 is Hooke's Law. And that's what we're talking about here. Let me get my pen back. Okay. Hooke's Law. One of the most basic principles relating to elasticity of solids. Now we're going back to elasticity, which was one of the properties we were looking at, and that's where we came up with our measurement of stresses and strains, because that's how we measure elasticity, with stresses and strains. Okay? And this basic principle related to elasticity is Hooke's law. What is Hooke's law? And named after Robert Hooke, by the way, a British scientist who was probably maybe half a generation ahead of Isaac Newton. He was still around when Isaac Newton got there, and Isaac Newton just flew past everybody. Some people sort of resented it. I think Hooke was one of them. Isaac Newton wasn't a particularly tactful person, so he didn't care if people resented it or not, and I think he rubbed them sort of the wrong way. So I think that he and Hooke kind of were at odds parts of the time. So basically what Hooke's law says, the ratio of the force applied to an object to change its length is constant as long as the elastic limit has not been exceeded. Now that's a weird way to phrase it, but let's see if I can write that down. Hooke's law says the ratio, and ratio stands for what? Comparison in a division sense. Okay? The ratio of the force applied to an object to change its length, resulting in either being stretched or compressed, depending on if it's a tensional force or a compressional force, by the applied force is constant. Now, the trouble is they're not making a real clear distinction. What's the ratio? The ratio is the force to the change of length. Oh, there it is. Okay. So the ratio of the force to the change of length. Because when you stretch something or compress something, you're changing its length. Okay? Now the symbol for change of length is delta L. Delta means difference in L. How much did that length change? What was the difference? Always final minus initial, generally. So this is a ratio of force. So Hooke's law says that ratio of the force, applied force, to the change of length is always a constant, up to the elastic limit. Okay? Now we'll get to that right here. But what do we mean by this? The ratio of applied force to the change of length is basically the slope of this line. And you see a line has a constant slope. Right here at the end, it's beginning to deviate some. Not quite straight line anymore, but there, right about there is the elastic limit. Now, I think I used this illustration before. Have you ever taken a spring from a ballpoint pen and been playing with it too much and sort of stretch it a little bit too much, and then it doesn't come back and be a spring anymore, right? You've passed the elastic limit. What you get to there is the plastic region. It doesn't come back to its original shape. The elastic region is when whatever you do, compress it or stretch it, it goes back to the original shape. That's Hooke's law. Is valid only in the elastic region. The applied force, the ratio of the applied force to the change of length is always a constant. That slope is constant. Up here, the slope is changing constantly. Now, some materials are elastic up to a certain point, and then you add a little more force to it, and they break. That would be a fracture. So for some materials, this would be where it fractures, and that would still be the elastic limit. There wouldn't be a plastic region, just the elastic limit region and then the fracture. So the elastic limit would be the point of fracture. Other things like that spring, it would actually deform first. If you keep pulling on it, it's going to break at some point. So that would be its fracture. But in between there, that would be the plastic region where it doesn't go back to its original shape. Now here's example 2. This is a spring, and it says a force of excuse me, 5.00 newtons is applied to a spring whose elastic constant is, and this, by the way, is the elastic constant. Okay? So whose K is, and by the way, sometimes it's called Hooke's law constant or Hooke's constant, is 0.250 newtons per centimeter. Okay? Now, notice that the units are okay, because force is measured in Newton and length is measured in any length measurement. This one happens to be centimeters. Okay? Now, find its change in length. Are we too much worried about we're not in SI units now? All we're looking for is change of length. If you use this formula this way, your change of length is going to come up in centimeters. Perfectly fine. In fact, that makes more sense than changing it to meters and having such a tiny change of length that makes no sense. So let's use Hooke's law, and what we're looking for, it says find its change of length. So delta L is what we're looking for. That's the unknown. Now, there's a couple of ways to do this. You can either use Hooke's law, which we printed here, as written, plug in the numbers and then get the result, or you can solve for delta L, what you're looking for, and then plug in the numbers and you've got the result. So which way you want to do? Plug and chug or chug and plug? I don't really care. Plug the numbers in first. Okay, we'll do that. Here's your formula, and that will be, let me copy it here. F over delta L is equal to K. So we know F is 5.00 newtons over delta L, that's what we're looking for, so we don't know that, is equal to 0.250 Newton per centimeter. Okay? So what you've got to do now, since you've chosen to plug first and chug later, let's chug now. You need to find delta L. Guess what? Being in the denominator is not the place to find it. You need to get it to the numerator. How do we do that? Multiply both sides. How do you undo division? Multiply. Delta L here and delta L there. As long as you do it to both sides, that's fair, right? Got to do it to both sides. Well, over here, they cancel out. And what we have left, I'm going to reverse sides here, is 0.250. I'm going to put the units down, though they're sort of in the way, times your delta L is equal to 5.00 newtons. Now what do we need to do? Oops, that's newtons per, no, this 2 point is Newton per centimeter, and this is just Newton. Sorry, I left off. Where? There it is. All right. All right, we're looking for delta L. So what have we got to do? Now we're undoing multiplication. How do we do that? Well, operation undoes multiplication. Division. So we'll divide both sides by our 0.250 newtons. Newtons per centimeter. I keep leaving off the per centimeter. Divide over here by 0.250 Newton per centimeter. Okay. Now, here, everything goes, and you're left with just your delta L. Over here, okay, I'm going to do something pretty close to what I did before. Since I don't have a calculator, I'm going to move this decimal 2 places this way, this one 2 places that way, And how many times will 25 go into 50? Pretty easy. 25 into 50? 2 times, and then 25 into 0 would be 0 times. So that gives me 20, but notice here, your newtons go out, and you're left with a 1 over a 1 over a centimeter. And when you do that in division, like, that's 1 divided by 1 over centimeter, which is the same as 1 times centimeters over 1. To do a fractional division, you invert and multiply. So this unit comes out being centimeters, 20 centimeters. Now I need to put a 0.0 in there because we had 3 digits coming in. You have to have 3 digits coming out. So our delta L is 20.0 centimeters. Does that make sense? Any questions? All those steps seem to do okay. Okay. I know they're all over the board there because I don't have much room to write on this board. So I write wherever I can. All right. So that's what they got in the book. Now in the book, they chugged first. They solved for delta L by making it delta L is F over K. And then when you plug in, you get the same mathematics, but you just get it directly. All right. Now let's see if they have the next slide. No, they don't. I think what we have to do here, we don't have to, but I'm going to, is go to a clean page. So let's discard this and go back to our white paper, whiteboard or white whatever. And here's example 3. A force of 3 pounds, I got to get my pen back, F of 3.00 pounds. Now we're no longer in SI units, we're in US customary. Stretches a spring 12 centimeters. So what would that be? What does that represent? That's your delta L, is 12.0 inches. Okay? What force is required to stretch the spring 15 inches? So now you're looking for a new force. I'll call it sub n. That's not normal force. New force. That's what we're looking for a new delta L. That'll be the new delta L of 15.0 inches. Okay. Now there are a couple of ways to do this. Okay. I'll do it the way the book does, which is a little bit longer, but it probably makes more sense using the formulas we have. If we know the original force and the original stretch, what can we calculate from that? What relates the force to the amount of stretch or shrink? What's that supposed to be? Think if I was a pirate. Hook! Hooke's law? Oh, okay. What does Hooke's law say? Relates the force to the change of length. The elastic constant. Okay? So what was the formula for that? We just had it. F over delta L is equal to that elastic constant. Okay? And we know, I've got to sneeze, sorry. Sorry, I'm right under a vent here. All right, so that is going to be 3.00 pounds divided by 12.0 inches. And what does that come out being? I think you can do that in your head, basically. Anybody? Isn't 3 over 12 the same as 1 over 4? And what is 1 over 4 in decimals? A quarter of a dollar is 0.25. So we need 3 significant digits, so 0.250 pounds per inch. That's the unit for your Hooke's constant. So now that we know that, same spring, so same Hooke's constant, as long as you haven't exceeded the elastic limit, and we'll assume we haven't, then we can come down here and find out the new force that stretches it the new amount. Same formula. F sub n over delta L sub n is equal to the same constant, K, which is 0.250 pounds per inch. Okay, and what do we know here? The delta L. So we got, do you want to do chug and plug or plug and chug here? Which one? Chug and plug? Okay, so we're going to solve for delta L first. How we're going to do that is multiply both sides by delta L sub n. Okay, they disappear here, which is good. I don't like denominators that much anyway. So you have F sub n is equal to K times delta L. But we're looking for, that's it, right there, isn't it? So now we plug. K is 0.250 pounds per inch that we calculated for, same spring, same constant, okay, times your delta L. This time the delta L was 15.0 inches. The inches cancel out. That's why it doesn't matter whether we have feet or inches. Wait, I got to wait till the thing comes back. Okay, there we go. So what's 15 times 0.25? Okay. I believe that's something like 3.75 or 37.5. No, 3.75, isn't it? 3.75, what unit? What unit? Pounds, because our inches cancel out, and that's a great unit for a force. Our new force is going to be 3.75 pounds. Does that make sense? Well, if 3 pounds stretched at 12 inches, 15 inches, just a little bit more, so this is just a little bit more. Yeah, 3.75, almost 4. So that makes sense. How did they do in the book? Yes, 3.75 pounds. All right. Okay with that? Let's move on to example 4. Can I erase? Okay, example 4 on page 322, bottom of the page there. A support column is compressed 3.46 times 10 to the minus 4th meters. Now, compression is a what? If the column is compressed a little amount, what is that? Change of? Okay. Think if this was a spring and you pushed it together. You change the length of the spring. Now it's a column and it's being compressed, so this is the change of L. Delta L is equal to 3.46, nice round number, times 10 to the minus 4, so that's a pretty small number, but it's a big unit, meters. So that's still being compressed a fair amount. Under a weight of, now what is a weight? Weight is a force due to weight, and that weight was 6.42, another nice round number, times 10 to the 5th, they like that, 10 to the 5th newtons. That's a good force measurement, back in SI unit, by the way. How much is the column compressed under a weight of 5.8 times 10 to the 6th? Whoa, 10 to the 6 newtons. Quite a bit more force. Okay? So the question is, how much is it compressed? So now we're looking delta L nu. That's your unknown here. When you add a new force, I'm going to call it F sub n, that's not normal force, but a new force of 5.80 times 10 to the 6th newton. So quite a bit more force. Okay? Really, we do it very similar to the last problem. The only difference is we're not looking for a new force, we're looking for a new length. So how do we do this? First step, anybody? Which equation is that? Force divided by the ratio of force to change of length is equal to a constant. So the first thing we do is find the constant for this support column. Okay? And we've got those just like that. So that's 6.42 times 10 to the 5th newtons divided by change of length, 3.46 times 10 to the minus 4 meters. Okay? This, folks, is going to be a big number. Because your numerator is already big, you're dividing by an incredibly small number, that makes the result huge. So, do you know how to do it using scientific notation? Your calculators will keep up with it fine. If not, I can show you how to do it. All you have to do is do your decimal numbers. So if you have a cheap calculator that doesn't have scientific notation, you can do it without the scientific notation. Do you want to see how? Or can you do it on just as you got it? It's up to you. How do you want to do it? Cheap calculator way or a fancy calculator way? Second? Cheap. Okay, here's what you do if you have a cheap calculator. Just divide the number part. 6.42 divided by 3.46. That's pretty easy to do. That's going to be 1.9 or so. Second? I can't hear. Oh, okay. 6.42 divided by 3.46. I'd say 1.9, but I'm guessing. 1.85, that's pretty close. 1.85 times 10. Now we have to figure out the exponents. Okay? When you're dividing numbers, you divide. When you're dividing same base, different exponents, subtract the exponents. So I put down the same base, 10, but subtract the exponents. 5 minus a minus 4, well, minus a minus is plus, so 5 plus 4 is 9. And that will be newtons per meter. You talk about a big Hooke's law constant. There is one. Because this is a column that supporting a building or something like this. Okay? So that's a huge constant. 1.85 times 10 to the 9th newtons per meter. So now that we know the Hooke's law constant, we can come down here and solve for your delta L n. What formula are we using? the very same formula. F, now it's the new force divided by the new delta L, is equal to the same spring constant, because it's the same building. It's the same column, okay? It's just being compressed under a bigger weight. And we know, now do you want to plug and chug or chug and plug? I don't really care too much. Help me somebody. You want to solve for delta L first and then plug in the numbers, or you want to plug in the numbers then solve for delta L? It really doesn't matter much to me. You tell me. Chug first. So we'll solve for delta L first. How would we do that? Multiply both sides by delta L sub n to get them into the numerator. Okay? This wipes that out of the denominator, which is a very good thing. And then what we're going to do, since this is what we're solving for, we're going to divide both sides by your k. Wipes it out here. So now we have delta L, the new delta L is equal to the new force, that's an ugly n, divided by the old k. K for both of them. So the new force was 5.80 times 10 to the 6th Newton, divided by, your K was 1.85 times 10 to the 9th Newton per meter. All right. So 5.8 divided by 1.85. If we do it the old calculator, the cheap calculator way, you divide those numbers, and my guess that's going to be between 2 and 3, right? 5.80 divided by 1.85, or is it closer to 3? Anybody with a cheap calculator? 5.80 divided by 1.85. Is what? .80 divided by 1.85. 3.135. 3.135. We're going to come back and change that in a minute. Okay? Times 10. Now, how do we deal with the exponents? Subtract the exponents. 6 minus 9 is minus 3. And then your newtons cancel out. And 1 over meter is a meter. And that's your change of length. The new change of length is that. Which, 10 to the minus 3 meters is millimeters. So that is 3. Now, here's where we make our change. We only have 3 digits. 1, 2, 3. Look to the right. There's a 5, so you move this up and make it a 3.14 millimeters. Because a 10 to the minus 3rd meter is a millimeter. That's how I would do it. How does the book do it? They come up with 3.12. Now, they probably rounded off worse than you did. So I'm going to go with your answer rather than theirs. It should be about the same. But when you're making that many calculations, it's easier to lose a digit or two. Okay. Pause this for a moment. All right. So don't worry about if you're off by just a couple of hundredths. That's not bad. I don't know where they made their error. Okay, there's a physics connection at the bottom of page 323, and that's development of materials. You can read that if you'd like. It's fairly interesting stuff. And that led to the next slide, which is just, let's say, put it in the system, we'll deal with it. But all right. What they're talking about in the previous page, development of materials, the guy is talking about here, and this is a bridge that was built back in 1779, and it's still a functioning bridge. And it's just talking about his cast iron bridge. And then they also talk about what they call pre-stress concrete. So you can study that or look at that if you want. They're pretty interesting topics. I doubt if you'll need much of that in diagnostic medical sonography. So it's just if you're interested in it. But they had the picture here, so I thought I'd tell you what the picture stood for. And there's the pre-stressed concrete. What they do, they put enormous tension on the rods there. They pour the concrete and let it dry. Now, when concrete dries, it tends to have micro cracks in it because water is evaporating when it's drying very slowly. So what was water now is air. So then they release the tension and it pulls the concrete together, so it makes it much stronger. Okay? So that's what this figure is showing. Okay. It's going to be a little while before we get to that one, but that finished problems are set 12.2. Homework exercises here would be any of the odds 1 through 9 in 12.2, then any of the odds 11 through 19 in 12.2. All those odds should have answers in the back of the book. So work on those. Those are going to be similar to what you'll see on your test. Okay? Now, properties of liquids. Okay? We were, that last section, 12.2, strictly solids. Now, what we did with liquids at 12.1 was talk about a solid is something that maintains its constant volume, constant shape. Pretty much constant volume. Shrinks or swells very little bit. Liquids, however, take the shape of the container, so they have indefinite shape, but they have a constant volume. Pretty much, most of the time. So let's look at some of the same concepts that we had with liquids, solids, that we also have with liquids. Cohesion and adhesion. Cohesion is the tendency of liquid particles to stick to the same particles, whereas adhesion is the tendency to stick to different materials. Okay? Now this cohesion, I guess I'll write it down. And so let's go back to the other slide, because this is going to be tough to write on that one. There wasn't much room. All right. Go back here and go back to, all right. Cohesion. Okay, I'm going to pull my thing back up. It'll take a minute to come back, I hope. There we go. Cohesion. Force of attraction between like molecules, just what I was saying before. Force of attraction between like molecules. Okay, and I think I gave this example before. Water has a lot of what they call surface tension. Water molecules stick to other water molecules really strongly, and that's why in the picture in the book shows a needle floating in a pool of water. Well, guess what? Steel is denser than water. It should sink, but it's the tension, the surface tension, the cohesion of the water molecules is strong enough force to keep the needle from sinking. Now, if you were to aggravate somebody by going and just touching it, you break the adhesion of the cohesion of the water molecules, and it sinks because it is denser. Okay? Adhesion, it's just like adhesive. It's the force of attraction between unlike molecules. The force of attraction between unlike molecules. Now, the example they give here is a rather dumb one, but it does work. If you stick your finger into molasses and pull it back up, molasses is going to stick to your finger because that adheres to your finger. There is a force of adhesion between your finger and the molasses. And then you get to lick the molasses off, of course, right? Bonus. Okay. But the same thing happens with water. You stick your finger in a pool of water, and it will also adhere. Now, here's another thing that you might find a little interesting. Let's go back to the cohesion of water molecules, the force that holds the water molecules together. Okay? And you put a needle on it, drop it in very gently, it will float on top. Now, this is something you can try at home, and I think you'll find it interesting. Get you a glass or something with water in it, and get a needle, a regular sewing needle, not a pin, but a needle, and very gently lower it onto the surface. Don't let your finger hit the surface, and that needle most of the time will float on the water. Okay? Then, get you a single drop of liquid soap, and off to the side, somewhere isn't going to make a ripple or anything, drop one drop of soap into the water. What soap does is a surfactant. It breaks that surface tension of the water, and now it's not strong enough to hold it up. That needle will sink, just like it would if you pushed on it. But that's what they suggest here. The surface tension of the water will support the needle. Adding the soap reduces the surface tension, the needle sinks immediately. So that is the next word they have here, is surface tension. I've been using it all along. They waited till now. Basically, it's the exhibition of cohesion. Okay? Surface tension, ability of a surface of a liquid to act like a film. Now, I don't know if you've seen water bugs skim along the top of the water. Surface tension is what's keeping them up. Otherwise, they would have sunk. There are certain kinds of frogs who have developed that technique too, and they skim along the top of the water. Don't try it yourself. You won't make it. But if you've ever done any water skiing, really that's what you're doing. The surface tension of the water, if you have enough force behind it, you are riding that surface tension. So it's the ability of a surface of a liquid to act like a thin, flexible film. Okay. Here's another characteristic of water. Viscosity, or property of water, I guess. Viscosity. Okay? Viscosity is the internal friction of a liquid. Caused by molecular attraction and these are usually like molecules, so that's cohesion again. Okay? Now, the place where most of the time you see viscosity mentioned, there's other places that use it, but it's in oils. Okay? Oils as in what oils you put in your car. I don't know if you've ever noticed this, or your lawnmowers or weed eaters or anything that a machine that you're going to put oil in to keep the engine lubricated, you'll notice that those oils usually have a number on top. 10W40, SAE 30, some sort of a number like that. That's indicating something about the viscosity of the oil. The internal friction of the liquid, in this case the oil, caused by molecular attraction. Okay, now here is the trade-off. Oils, when they get very cold, get very stiff. Okay, now this isn't an oil, but it acts like one sometimes. Think that same, what we're just talking about, molasses. If you put the molasses in the fridge and bring it out, try pouring that. It hangs right there and maybe very slowly pours. It's hanging together with great thing. But if you heat that molasses up, as in just in a pan of warm water, it will pour much, much more quickly because it depends on heat. Oil's the same way. When it's very cold, your oil will almost tend to coagulate and not lubricate as well as it's supposed to. But if it's too hot, then it's so thin, it doesn't lubricate well. You need it in that middle range. So that's why in very hot climates or very hot conditions, you want a large viscosity because it tends to be more viscous and hangs together better. But if it's going to get very cold, you want a low viscosity oil so that you can still lubricate. If you lived up north, like way up north, Minnesota, they have to change their oil with season. They get almost as hot in the summertime as we do. They don't stay hot as long, and they're, various things like that, but they get very hot. So they use a low viscosity oil in the summertime, a high viscosity oil in the wintertime. No, I said it backwards. High viscosity oil in the summertime, low viscosity oil in the winter. They have to change it, otherwise their engines don't work well. They'll freeze up, they'll break down. Okay. Down here we use what they call blended oils. That's what I said before. 10W40, 10W30, those are blended, so they have some high viscosity, some low viscosity, and the range. And we don't get that cold in the wintertime. We get pretty hot in the summertime. So get one that's viscous enough for summertime. It'll usually go all year. Okay. Another characteristic of liquids is capillary action. I can't write tonight. What is wrong here? Okay. It's been all day. It's not just been tonight. Whoops. I hit the wrong button. Okay. Capillary action. Okay. Now this is something that I bet you, aren't most of you in the medical field already? No, you're not. Okay, get ready for it because you will be dealing with this. Okay, where do you hear the word capillary? Yes. What is happening, you have arteries that basically transport blood until you get to the place that's really going to use them. Then the arteries get smaller and smaller and smaller until they actually become capillaries. And at the capillary stage, where they're very, very thin, then the blood can exchange oxygen, nutrients, and other things, like when I say nutrients, sugars and things like that, with the muscle that's needing it. And then the capillaries start getting bigger again, and they go back through the veins and take it back. So the big veins that you see are things that are transporting the big arteries that you can feel your pulse. Those are the transport systems. That's not using it. The capillaries, that's where the action is. Very thin, very thin walls. So capillary action is behavior of liquids that causes the liquid level in very small diameter tubes to be different from large diameter tubes. I'm not going to write all that, but you can read it from your book. Behavior of liquids in varying diameter tubes. Okay? Now, pictures are worth thousands of words, so let's go to the picture. Okay, this picture is going to show several things, and we'll focus on the ones we want now, and we'll use the rest later. Okay? Let's just look at the very first one right now. Well, actually, this really applies to several things. Okay. Here you have water, or any other liquid, but we'll deal with water. Okay? Now, to start off with, I have no idea why they have different colors in here. That doesn't matter. I don't know why they're different colors. They shouldn't be. Should just be the same color. But so don't worry about the colors. Okay? If you have a big tube here holding the water, then it'll have a small rise. Now, why does that rise? It goes back to the two things we talked about at the very beginning. Cohesion and adhesion. The first thing that's happening here, water likes the wall of the glass. So it tries to crawl up. That's adhesion, the attraction between unlike molecules. So the water molecules like the glass, and they adhere to it, and they move up the sides. As they move up the sides, because they cohere to other water molecules, they pull the other molecules up with them. So you have both of them going on. Adhesion with the sides and cohesion pulling the other molecules up. So you get this, and we call this a meniscus, okay? That curved surface there, and that surface is concave, like the mouth of a cave. It opens down, okay? You put a smaller diameter tube there. Now, the water molecules going up the edges of the small tube, they're closer to all the other water molecules, so they pick up that center molecules higher, because that cohesion of the other water molecules, you see the area around here is far apart, so the water molecules can only pick up so many other water molecules. Here, where they're closer together, that many molecules, they can lift them higher. Okay? So again, adhesion with the wall of the tube and cohesion with the other molecules, they rise higher. Okay? Then you put a really tiny tube in. Think of this as being your capillary. Okay? And then it raises way up there. I think this is pretty exaggerated, but they're doing it for a point. Now, have any of you either taken blood samples or have seen someone take that, when they go in and prick the finger and then pick up a little thing, which is really just a capillary, and hold it right there, and you see the blood just go right up? That's capillary action, because it's a very, very thin tube, and the blood adheres to the glass in those tubes and sucks that blood right up the tube. Then they can go and apply that to things. They don't have to, everything's sterile there, you don't have to mess with anything. So that's what we're talking about. Adhesion, cohesion, adhesion, cohesion. Okay. And that illustrates capillary action. The smaller the tube, the higher the rise in the tube. Okay. Now, On the other hand, you sort of have the reverse happening when you have a material that does not adhere to the glass. And one of these materials is mercury. Mercury hates being close to the glass. It has absolutely no adhesion at all. In fact, it coheres to each other, and it tries to stay as far away from the glass as possible. So you put a tube down in a pool of mercury, and it actually sinks because the mercury on the inside and outside tends to stay away, but on the inside of the tube, it actually pulls the other mercury down. That's all cohesion. There's no adhesion here at all. So the meniscus is downward. That surface is convex. The meniscus is down. Put a smaller tube, it pushes it down even further, because now all these are pushing down on it, so it's down there. Put down a capillary tube, and it's way down there. Now, they don't show this as being very convex here, but it should be. The picture just didn't come out too well. Okay? So that's the reverse of capillary action when you have materials that do not adhere to the walls of the container. Okay. And I've already mentioned the term meniscus. They didn't mention it here, but that is the crescent-shaped surface of a liquid. Let me get my pen back. Okay. And in general, when you're reading the level of a meniscus, this is more of art than anything else, you usually take the lowest part of a concave surface or the uppermost part of the convex surface, because otherwise you don't know where to go. So go to the minimum here, the maximum there, and that's where you usually make your readings. By the way, where's another, in medical terms, where's another capillary that you're sometimes having to read that meniscus? Under your tongue? Thermometer. Now, nowadays, they have machines that do everything for you. But in the old days, that was either, if it was a silver liquid, that was mercury in that thermometer. And you'd read the top of the meniscus there. And that's where you measured the temperature there. But if it was a red liquid in there, that's probably colored alcohol, and that's more like water. You would read the lower part of the meniscus there, the minimum there, and that's how you'd read it. That's what it was calibrated for. Most of the things are electronic now. You don't have to read anything. You just read the numbers off the screen. It's not like it used to be, is it? Okay. All right. Experimentally, scientists have found that liquids rise in capillary tubes that tend to wet, depressed in tubes that tend not to wet. In other words, if the tube will not be wetted by the liquid, it depresses it. If it will be wetted by the liquid, it raises it. Elevation or depression in the tube is inversely proportional to the diameter of the tube. That's what we saw there. And the elevation or depression decreases as temperature increases, because now the molecules, liquid molecules, are moving with more energy. They don't hang together as tight, either pushing down or pulling up. All right. That was 12.3. No examples or no exercises in that. 12.4 is the shortest section in the chapter, I think. But it does have a few terms, so let's go to yuck. It's not what I wanted. I wanted to do that. Okay. Properties of gases. Okay. Let me get my pen back. I do this every time. Properties of gases. I should have initiated my liquid thing with this too. Properties of gases. Now remember, gases take the shape of their container and have no definite volume. No definite shape, no definite volume. So one thing that gases do more than liquids or solids, so they do them too, but this is so much more, that is expansion, okay, is a property of a gas in which the rapid random movement of molecules causes the gas to completely occupy the volume of the container. Now, we're not talking about expansion when heating and contracting when cooling. We're just saying you open a bottle and let the molecules go, they fill up the whole container. Exactly what we're talking. They take the shape of the container and they have no definite volume. They fill the whole room. The example I gave of opening a bottle of ammonia in the corner and then leaving, y'all are going to start noticing it very soon. Okay? Now, here's another one that could have applied to several things, but we're mentioning it now, is diffusion. Okay? Let me fill out for expansion. Property of a gas, the rapid movement of molecules, okay, cause it to fill the container. I can't write. Okay, what we talked about before. Diffusion. The process by which molecules of a gas mix with molecules of a solid, liquid, or another gas. Process of mixing with other molecules. Okay. Now, like I said, this would apply to several things, not just gases, but let me give you my layman's term or definition or example of diffusion. I like to work out in the yard. You know, I enjoy messing with plants in the soil and doing things like this. So I've gardened a bit before and other things, and I've noticed one of a gardener's biggest nemesis is Bermuda grass, right? And if you've ever noticed, Bermuda grass, you want it in your yard because it makes a good yard grass. You don't want it in the flower bed or the vegetable bed or wherever. But what does Bermuda grass do? If it sees that, it heads toward the other. What diffusion is going down a concentration gradient. Now that's big fancy terms. What it means is something will move from high concentration to low concentration. You have lots of Bermuda grass in the yard. You don't have any over in the flower bed. There it goes. Okay, it sends those things out there and starts occupying the flower bed or the vegetable bed. That's diffusion, going from high concentration to low concentration. They don't define it quite that way here, but that's exactly what you're dealing with. Okay, process of mixing with other molecules, and it travels down a concentration gradient from high concentration to low concentration, just about always. Okay, one other term they have here, properties of gases, is just a term, a general term, a fluid. A fluid is a substance that takes the shape of the container And guess what? That could be either a liquid or a gas. A lot of times we think of liquids as being fluids. Gases are also fluid. The same principle that governs the flow of your blood through your veins and arteries, the flow of water through a pipe, same principle applies to the flow of air through a duct. Same principle. They're both fluids. Okay? So that's the only deal there. Both liquids and gases are classified as fluids. All right. Now, because it's so important, we're going to devote an entire section here to one property. And that's going to be the one that occupies the rest of the chapter. And that is the property of density. So I think I'll start a new page on this one. Okay? Yeah, I might as well. Density. Okay. It's a property of all three states of matter, or phases of matter. Okay? There are actually two types of densities we deal with. Mass density, and that's mostly in the SI units, and this book uses D sub M for mass density. It's mass per unit volume. Yeah.
I have to leave. Can I turn my disc into it?
Yeah, sure. Yeah, several other people have already turned theirs in. All right, good deal. I don't think we'll finish chapter 12 tonight because we don't have that much time, but next time we will, so that you'll be getting chapter 12 test next time.
Okay.
So mass density is mass per unit volume. What units would that be? What's the SI unit for mass? Anybody remember? Units are important, folks. Kilograms, that's it exactly. Say again? That is exactly right. And what's your unit, the basic unit of volume in the SI units? Remember, volume is length times length times length, so that would be lengths are meters, cubic meters.
I have meters.
Okay, meters would be length, and since you're doing length by length by length to get volume, that's cubic meters. So kilograms per cubic meter would be your basic unit of density in mass density in the SI system. We don't usually talk about mass density in the U.S. customary system because we don't talk about mass in the U.S. customary system. That unit is slugs and no one uses it. So we usually don't use it there. Okay? On the other hand, there is weight density. Now this could be talked about in either unit, and this is usually D sub W, and that would be not mass, but the weight, which is force due to weight. F sub W is what this book uses per unit volume. So this would be mass, I can't write, per unit volume, and this would be force per unit volume, or weight per unit volume. Now this is mostly used in the U.S. customary. What's your unit of force in the U.S. customary system? You stand on the scales? Pounds. And then we use all sorts of different things for the volume, which is, again, length on length on length. What's your basic unit of length in the U.S. customary? Okay. Meters is in the SI system. It would be usually feet.
So, I heard you wrong.
Okay, sorry. So it's pounds per cubic feet, but we also use pounds per cubic inches sometimes. Okay? But that's a pretty small unit, so more likely it's pounds per cubic feet. Okay? If we did use weight density in the SI system, and you could. What's the unit for force or weight in the SI system? Not pound, but Sir Isaac?
I have Newton.
Newton. And then what was our unit there? For volume is still cubic meter. A Newton per cubic meter. Okay? All right. And in the book, they give, for the metric, SI, I'm sorry, I got to sneeze again. Sorry. Scaring people at home. Okay. It would be kilograms per cubic meter, and mostly in the U.S. system, it's pounds per cubic feet. And the table I'm going to show lists both of these units. But I wanted to mention just a few of them right now. Okay? The mass density of water, and it seems pretty incredible. So that's D sub M for water, H2O, is 1,000. Now they put a bar over the middle zero. It's 1,000. Okay? It doesn't matter what units. Kilograms per cubic meter. And the reason for that is that it's a round number, is when they first identified the unit for mass. They took water as the standard thing that was the most common substance on the surface of the planet, and they took water, and 1 gram of water, they said that was what 1 cubic centimeter of water was. That's how they defined it. And then when you do your unit conversions, that gets you up to 1,000 kilograms per cubic meter. So that's where that came from. The density of water is exactly 1 gram per cubic centimeter, because that's how they defined a gram, is the mass for 1 cubic centimeter of water. So that's sort of a side note there. And by the way, a cubic, I'll leave that alone. The weight density of water in the U.S. customary, D sub W for water, H2O, I can't write, goodness gracious, happens to be 62.4 pounds per cubic foot. Okay? You'll use that a lot, but you can always look it up in a table. It's not worth memorizing. Okay? And that leads us to the next table. And that's on this slide set. Let's go from current slide to here. Here's the table. It may be hard to read from where you are. You can read it more easily from your book. But I just wanted to point out a few things in the table. Okay, starting with solids. And I think we looked before. I couldn't find a periodic table in the book. I wish you could, because you'll find that the things at the top of the periodic table, the metals at the top of the periodic table, like aluminum, are very low density. 2,700 kilograms per cubic meter, or 169 pounds per cubic feet. Now, it may sound like a lot, but that's a pretty low density for a metal. Brass, which is a mixture of copper and tin, I believe, that would be much denser. Okay, mass density of 8,700 kilograms per cubic meter, 540. Okay, pounds per cubic feet. Concrete, which is a mixture of sand and cement and a little bit of water, it's not nearly as dense as it's almost the same as aluminum, but not as dense as brass by any means. 2,300, 140. You don't need to know these. I'm just pointing them out. Cork, which is that certain type of a wood material from a certain type of a tree, that floats. I mean, they used to use it for fishing lures, fishing bobs. Quartz is down at 240 kilograms per cubic meter, or 15 pounds per cubic feet, which you'll notice is a lot less dense than water. Let's go on down and look at water. 1,000 here and 62.4 there. So that's why quartz floats so nice. Ice, which is a surprising thing here, but you know it. But if you think about it, just about every liquid, when it cools and forms a solid, it gets smaller. Water is about the only substance on the planet that I know of that when it freezes, it expands. Strange, but true. Part of that is because of the crystal structure of water. Part of it is because of that cohesion of water molecules. When it's a liquid, those molecules hang together so tight, they're dense. But when it starts freezing, then it moves into its crystal structure, and the crystal structure actually forces the molecules further apart because of the nature of the crystal. So that's why ice floats. And if it were not for that characteristic of water, strange, unusual characteristic of water, life on this planet would not exist. Really? Because then, if it froze and sunk, ice would freeze from the bottom of a river or lake or pond or ocean from the bottom up. No life would be able to, And if you don't have the fishes happy, nobody's happy. Okay, so believe it or not, that would affect us all. Okay, so amazing. Okay, so ice is slightly less dense than water. 917 versus 1,000, 57 versus 62.4. Okay. Iron. Now, iron is much denser than aluminum, concrete, most of those, but not as dense. I skipped copper before. See, copper and brass are close together because copper is in brass. Okay. Brass is an alloy of copper and zinc, and without a periodic table, I can't show it to you. But I said zinc. I think it's 10. And 10 is fairly close to copper as well, so it's right down there in the same ballpark. Iron is not as dense as those two are, but it's much denser than aluminum. Okay? Lead, one of the densest of the metals. Okay? And that's why they put lead sinkers to drop the hooks on your fishing. I'm not a fisherman, but I've been around enough to know. So lead is very dense, 11,300. Look at that, compared to any of the very dense, 708 pounds per cubic feet. Wood on general, this is white pine, which is usually a fairly light wood. It's less dense than water for sure. Not as light as cork, obviously, but less dense than water, so most wood floats. There is a type of wood called ironwood that's really, really dense, and some of that will actually sink, but most wood will float. Now, let's go to the liquids. Alcohol is less, we compare everything with water. Less dense with water, so it will float. Gasoline less dense with water, it floats. That's why when you have an oil spill or a gas spill, that liquid comes to the surface and you get that sheen, that colored looking sheen on it. And that's bad for animal life in the water because it blocks oxygen from mixing in, and if you have too big of an oil spill, things start dying underneath. And, even things like ducks and stuff, their feathers and stuff are made to repel water, but when you get oil mixed in it, then they attract that and they tend to sink and drown too. Okay, so gasoline floats. Now here is one of the, if you thought water was strange, mercury. Mercury ought to be a solid. It's a metal, it's a heavy metal, and yet at normal temperatures and pressure, it's a liquid. And it's even denser than lead. If you had a lead weight, put it in a pool of mercury, it's going to float. Believe it or not, it will. Okay? Oil is a lot like gasoline, and alcohol is denser than either of those, but not by much, but not as dense as water, so oil floats too. Seawater is a little denser than fresh water, okay, because it has dissolved salts, which are denser than water molecules in it, so it's a little more dense, 64 pounds per cubic foot rather than 62.4. Now, gases, you have to specify not only what you're talking about with the gas, but also what temperature and pressure it's at. So we're going to use the freezing point of water and 1 atmosphere of pressure. 0 degrees Celsius or 32 Fahrenheit and 1 atmosphere of pressure. Normal air, which is a mixture of all sorts of gases, is very, very light. Okay? Very light. Ammonia, even lighter. Okay? Carbon dioxide, a little denser. Okay? So carbon dioxide would tend, if you I don't want to get into too much here, but I'll leave that alone for now. Carbon monoxide is not quite as dense as carbon dioxide because it only has 1 oxygen per molecule rather than 2, so it's lighter. In fact, it's lighter than air. Helium is next to the lightest of the gases, 0.170. All the others are greater than 1 except ammonia, but this is 0.170. The very lightest gas is hydrogen, 0.0899. This helium is almost 4 times heavier than hydrogen. So the earliest blimps or dirigibles, the earliest flying machines, they filled them with hydrogen because it was the lightest gas. Does anyone remember why they quit using hydrogen? Does the Hindenburg come to mind? Bring a reason to mind. Zeppelin, okay? Not Led Zeppelin, but okay. What a Zeppelin was, okay, was I think it was a German name for a dirigible. But what happened with the Hindenburg was it was filled with hydrogen, and it was a stormy day, and it was being blown around, and it either hit something and ripped it, and there was enough friction to ignite the hydrogen, because hydrogen is an explosive gas. And that thing went up into a ball of flame like you wouldn't believe, because there's oxygen in the air, and it burned the hydrogen. Or it got struck by lightning, same effect, but it just exploded and killed probably everybody that was in the car. Okay? So after that, they started using helium. Helium doesn't react with anything at all. So therefore, helium is much safer than hydrogen. But it's not nearly as low density, but it's lower than anything other than hydrogen. The nitrogen is awfully close to air because air is mostly nitrogen, about 80%, close to 80% nitrogen. Oxygen's a little denser, and that's the next biggest component, so that's why air is in between nitrogen and oxygen. Propane is a little bit denser than oxygen and nitrogen, okay? So that just gives you the general gist of your densities. You will be using this table when you're solving some of your problems. And speaking of which, let's see if we can get one problem done in this chapter before we move on. I think we can probably do it here. Find the weight density of a block of wood, and this block of wood is, let me get my pen set up. Okay, 3.00 inches by 4.00 inches by 5.00 inches. As a block of wood. Okay. So what does that tell you? If you have the length, the width, and the height of that piece of wood, what can you determine from that? Not area, volume. 3 dimensions. So, let's see, the easiest way to do this would be 4 times 5 is 20, times 3 is 60. That'd be 60.0 cubic inches. Okay? With a weight of 0.700 pounds. So the F sub W, forced due to weight, is 0.700 pounds. Okay? Now, because the standard weight density is given in pounds per cubic feet, we need to convert this cubic inches into cubic feet. Do you remember how to do that? Multiply by a conversion factor, and you want it to become cubic feet. Okay? Always put the units in their place. One goes on top, one on the bottom. Which goes on top, which on the bottom? Inches or feet? One on top, one on the bottom. Tell me. Inches on top? That way then you would multiply, and that wouldn't work. You need to divide. Inches on the bottom. Feet on the top. That's where you want the feet to be on top out here. Okay, and how many feet in an inch or inch in a foot? You know that one, right? What? 12 what? 12 inches is 1 foot. Okay? Now we've got to cube everything. Yuck! Cubic feet, cubic inches, cubic 1, that's going to be 1. But 12 cubed, that's going to be a pretty big number. That's 144 times 12. If you got a calculator, do it for me so I don't have to do it. Second? 1,000. Okay, I'm sorry, this is a 12 cube. 1,000 what? 728. Okay, so take 60 and divide by 1,728. Second? I think you did the other way. 60 divided by 1728. Better come up with a pretty small number. 0.03. Okay, a little bit louder. 0.0 what? 35. Need one more digit at least. 347. Okay, we'll live with that one. You need at least 3 digits. You could do more if you wanted to. All right, so that's your volume, and your density, and this is a weight density, is weight, which is forced due to weight, divided by volume. And that would be 0.700 pounds divided by 0.0347 cubic feet. Okay? Punch that in your calculator and see what you get. Something a little bit greater than 200, isn't it? No, yeah, I think so. 20.2. 20.2 what units? Pound per cubic foot. Now that's a block of wood. Over here we said white pine was 26 pounds per cubic foot. So this must be a block of wood that's a little bit lighter than white pine. Okay? Does that make sense? What they got in the book, good for them. So I think we've run out of time. So we'll start with example 2 next time. Let's see if we got any homework exercises to do here. I think you can do number 1, and we'll wait and do the rest of it. So do number 1 on page 336. Okay? Now, any questions? Good deal. Thank you. Thank you. Boy, y'all are good at getting things in. Of course, we're missing 2 people here tonight, so they didn't get them in, but way to go. All right, we'll shut it down. We'll see you next week.